Great. Thank you. So, as we already saw, well, linear methods are kind of boring. They're very powerful, but ultimately, not everything in life is linear. So, let's look at preprocessing first. Who of you has done computer vision at some point? Okay, fair amount of you, right? So you probably know about the SIFT and the SURF and all sorts of other feature extractors and the candy edge detector and probably 10 other things that you could use, right? And you will basically inflict that upon the poor image, and then you'll get stuff like this out of it. So this is maybe the original image, and then maybe you get something that just detects edges in a particular direction, and maybe you get this, maybe you get the noisy version, God knows. There's an entire tradition of results that you could possibly obtain, right? And so this is actually all preprocessing, and a lot of the lore of computer vision until recently was essentially to design really clever filter banks and then just build relatively straightforward classifiers on top of it. So the thing that's been happening over the past decade is that people effectively realized, well, rather than using hand-engineered, hand-tuned filters, we can actually go and learn those filters. And this is, for instance, what all those convolutional layers in a deep network would do for you. They would basically extract really good filters, really good features from it, and then possibly on top of that extract other features and then work on top of that further. But ultimately, a non-trivial part of the success in computer vision is due to the fact that rather than having hand-tuned, hand-engineered filters, you can actually learn the stuff. The fact that you might actually find cats in the entire process had a lot to do with the fact that a lot of people on YouTube upload cat videos. So, okay, so it makes sense to actually do something interesting with cats. Okay. So, regression. So basically, we already did this, right? We even did this in the homework. We looked at polynomial features. And so basically, we get nonlinear functions very simply by taking the original data and, mapping x. Just a moment. So I map x into 1, x, x squared, maybe x cubed, and so on. And that, of course, will give me nice nonlinear features. By the way, I can do the very same thing for the perceptron as well, right? All I have to do is I just take my data and map it into a higher dimensional space, and then I get a nonlinear separator. Then I just solve the problem in the space. So this is now where things like this inner product part became interesting, right? Because before that, we had all this inner product between x and x prime, and I said, well, this is an insanely inefficient way of writing your code by actually writing inner products where I could just store features directly. But now I could actually go and do a query replace of all the inner products between x and x prime by phi of x and phi of x prime in the code, and I'm done. And if you had done this about 15 years ago, maybe 20 years ago, you could have written a lot of interesting papers. Basically, take a paper from the 60s that is linear, do a query replace of x by phi of x, and instantly you have a new paper. Unfortunately, that has pretty much been done. Even in economics, that has been beaten to death by now. Not to death, but actually there's some very nice work by Sébastien Lahaye. So if you're an economist, you want to check out this guy. He's actually done really nice work there. And so now you just have, rather than a perceptron, a feature perceptron. Okay, let's have a look at what this looks like. Okay, so here's the original data. And as you can clearly see, if I want to separate circles from x's, well, I can't really find a nice linear separator there, right? There's no way. However, I can map this into maybe a three-dimensional space where maybe I have as features x1 squared, x2 squared, and maybe I have x1, x2. Well, why are those relevant? Because if I want to, express an ellipsoid, I will have exactly those features. So more to the point, if I want to express this ellipsoid here, well, what would I do? I would do something like, well, x1 squared plus maybe 2x2 squared less equal than, I don't know, maybe 1. And that might give me a very nice ellipsoid. So I can do this here. So I've just made this mapping explicit. And so now, taking the original data, mapping it into this higher dimensional space, will actually allow me to perform linear separation in a nonlinear space of features. So the key point is, all of our algorithms, all of the math that we just did, goes right through. All I'm doing is I'm just pre-processing things. Okay. Now, that's actually something that people have done, and if you think about it, that's what your canny edge detector and your SIFT and your SURF and whatever other features you might want to inflict. Let's try that for things like OCR. So what I could do is, if I want to recognize the 10 digits, I could just count, how many loops, 3 joints, 4 joints, angles of a certain kind, acute angles I have. And, how much ink, basically, how dark the image is. And if it's just, a given character set and I always have everything perfectly, this might actually just work. Can somebody tell me when this can go horribly wrong? When could this go horribly wrong for optical character recognition? So with handwriting, yes, all bets are off because, for instance, if you're European, you don't write the 1 like so, you write this. That's a European 1. That's a European 7. Right? More than that, if I have a 0, people write it like so, they write it like so, or, do all sorts of other things. They might even write it almost like this way. So in other words, I have a lot of variations. Okay. Here's another thing that can happen. If this is actually handwritten, then maybe, this is on like a notebook, and this notebook gets dirty, or maybe somebody drips some water on it, and, it just gets messed up. So it's not so nice and crisp anymore. It may be entirely washed out. Maybe the camera module has a few dead pixels. So a lot of mess can happen that will break this entirely. So this is why explicit feature engineering, in many cases, will not get you amazingly far. That said, people still do that. In some cases, it's a really good idea. So, for instance, physicists are effectively amazingly good at feature engineering. When they do this, it means they essentially discover natural laws, because they actually go and, invent or describe or discover or derive equations for certain properties. And those equations hold exactly, and they are effectively, therefore, then conditions between fairly meaningful features that describe reality. Okay. Now, you may not necessarily have that in quite so much detail for most other systems. So, for instance, for email, if you look at that, this is basically the entire header of a very simple email. This is basically somebody sent me an email, and all of this is machine generated. So it contains stuff like, IP numbers, dates, and so on. So when the email was sent off, from which IP number it was sent, what time of the day, what the entire path was that the email took. Lots of other stuff. There are sometimes, cryptographic mechanisms in there to, prevent emails from open relays to get through. So there's a lot of technology that's happening behind the scenes. And then the email was, I think, something like, can I submit my homework a day late, right? But this is all the trace that's being generated from that simple email. Okay. And of course, you can use that for a lot of feature engineering. In some cases, it's good. So for instance, suppose I have a script kiddie who realized that, okay, you sign up for an account and then an hour later you send out spam. So then the first thing you want to do, if you know that this script kiddie will always send out the spam exactly 60 minutes late, the very first thing your site reliability engineer will do is actually throw up a rule to just eliminate all emails sent out exactly 60 minutes after the account creation. And then maybe half an hour or an hour later, somebody will actually come in and use some machine learning tools to find a more permanent solution. But the first thing you can do is actually, a very simple set of features that you can extract by maybe a bit of detective work from it. And this is actually where a lot of, engineering goes into. So if you work for a product team, you may end up doing a lot of this, sometimes without even noticing that that's what you're really doing. Now, there's, a lot more feature engineering. So for instance, if you have two interlocking spirals, right? Let's do this. And have another one. And I want to classify, whether it's red or green. Then in Cartesian coordinates, this is extremely hard. In polar coordinates, it's fairly easy. I basically transform things into an angle and a radius. And then it's a very simple, set of stripes that I can pull out from there. So if you, write Japanese characters, or I assume it's very similar for Hanzi, so you would probably have in a dictionary, if you want to look up the character, you have a certain order in which various strokes can be looked up. And effectively, that is very straightforward feature engineering of trying to understand which character is which. And that works really well if you look at the new character, in which order it needs to be written. But for all mortal humans, it's really hard. So you can't really do that. For medical diagnosis, physicians' comments are quite useful. Blood status, ECG. So there's a lot of explicit features that you can extract. Sometimes these features are extracted by poking a needle in somebody and pulling up blood and running it through a device. Sometimes they can be slightly less invasive. Preprocessing is really important, and I guess you've probably already noticed that in some of the homeworks. That by extracting the right feature set, you can actually improve your performance a lot with the same algorithm. So this is, for instance, what Pablo talked about for homework 2, where he explained, that moving into Fourier domain and essentially applying a low-pass filter really helps. So, zero mean, unit variance are often good things to make sure everything is actually reasonably well calibrated. Probability integral transforms, other things like that are really useful. Okay. And so, if we do this, we end up with a feature perceptron. Right? This is very, very, very simple and straightforward. It's the same algorithm as what we had before, with just one difference, that rather than having x, I have phi of x. Yes?
I have this question. What if your classifier boundary is essentially, when you define x, you're taking power series, right?
Okay.
So what if your classifier boundary is not a power series, it's more like a Lorentz series? So it's square root of x is your classifier boundary.
Okay. So that's another set of features. You could use that too. So if you knew that this is where your classifier can be found, so, some other series expansion rather than a power series, yes. So for instance, in many cases, people use a Fourier basis. Sometimes people use a wavelet basis. So that really depends very much on where you think your solution can be found, where you're able to find really fast and cheap expansions. So Fourier transforms are usually your friend because you have the FFD. There are other things that you can build on top of that. So for instance, if you want to know more about specific expressions of that type, do a search on for fast food on Archive, and you'll see a paper that we just submitted on how to extract certain sets of features very, very efficiently. So there's a lot of explicit feature engineering that you can do to obtain very, very rapid expansions. Or, for instance, there's a nice paper by Rasmus Pach on doing similar things for polynomial kernels, which uses essentially convolutions. Then again, the Fourier transform at some point comes in. Usually, there's a lot of reason for using very specific transformations because you just have a fast library. Or you have very talented students to implement a fast library. Right? So that's essentially what you can do. So nothing really is different from what we did before. The only difference is that now W is given by a linear combination of phi of xi's. Remember, before we had W equals sum over I yi xi, and now we have W is a sum over yi phi of xi. And where before we had just an inner product between xi and x, we now have phi of xi dot phi of x. So it's really the same algorithm. It's almost not worth really mentioning. Okay. Can somebody see what could go wrong with that feature extraction? Okay. I mean, effectively that question was a little bit related to that. Can somebody else see what could possibly go wrong with that?
So you could have major features so that a problem is unsolvable.
I could be yes, that's exactly what it is. So it could be that simply I'm too stupid to find the right features, that I don't get the right idea. So for instance, if I don't get the idea of looking at the Fourier transform of the data in homework 2, it's a little bit less easy. You can still do things with it, but it's a lot less easy. Right? So it's exactly that problem that we don't really know what good features are. So basically, quite often you need a domain expert. So I would do a horrible job at building a Chinese or a Japanese OCR system. Right? So I would almost certainly, as the first thing, go to somebody who actually has learned writing in that language and then ask them for features. Sometimes those features are extremely expensive to compute. And it's really, really hard to transfer the knowledge from one system to another. Right? And sometimes the people who you interact with may not actually want to tell you all the knowledge because it's basically job security. Don't underestimate this. So one solution that you can do instead is, because we don't know which feature is good, I'll just take a lot. So essentially, maybe you're not a terribly good shot, but if you take a shotgun, you'll probably kill the bird. Not because you're particularly good, because basically there's so many bullets, one of them is going to hit it. So you compute a lot of features, and you just hope that one of them isn't too horrible. And now, of course, it's the same thing like with a shotgun, where you can fire off a lot of bullets at once without really having to do a lot of work. We need to have an efficient mechanism of getting all those features very quickly. And I want to do this efficiently because otherwise I will be spending a lot of computational power on actually computing them. So a lot of the recent work on nonlinearities is on how to get those features in a computationally very efficient manner, possibly, for instance, by randomized algorithms. Okay. Yes?
Are there any properties of phi of xi that you need to consider in terms of course, you need to define the inner product now. Other than those, are there anything else that you need to
Oh, okay. So basically, the question is, what makes some phi of xi a good phi of xi? So first of all, they need to be in a vector space, but that's kind of the bare minimum, such that I can actually have a well-defined inner product. Other than that, in principle, anything is fair game, except that if it's very slow, it's not a good idea. Okay. Now, on a slightly more abstract level, what happens is, of course, your choice of phi of xi induces a certain function class. So, for instance, if I have phi of x to be 1x, x squared, x cubed, and so on, it basically means that I'm effectively estimating my decision boundary as a Taylor series expansion. If I have phi of x to be the Fourier basis, that basically means I'm actually preferring, for instance, functions of that are slowly varying. So my choice of phi of xi will have a lot of influence on what the functions look like that I will get out of this. And by being very smart there, I can get way better solutions. So we'll actually get to a slightly more formal treatment of that as we now go to automatic ways of generating those phi of xi's. But yes, effectively by picking the features, you're going to pick the function class that you're going to look at. For instance, think of medical diagnosis. If one of your features is the heart rate, then you can probably diagnose all sorts of things about your heart beating really rapidly or beating very slowly, right? If you don't have that feature, that decision boundary will be very, very hard to establish otherwise, unless you take EEG data and then ECG data and then actually extract some features from that amount to heart rate, right? So this immediately tells you that you can screw up very badly by designing the wrong features. So don't underestimate this. Okay. Now, of course, there's a better way. Kernels. So Grace Waber, she is one of the key contributors to that area. Her papers are brilliant. Her talks are interesting. She wrote this wonderful book in the 90s about spline models for observational data, which doesn't sound like kernels at all, but it essentially has kernels in there. There are other people like Aronson and so on who basically introduced what's called the reproducing kernel Hilbert space in the 50s. So this is actually a useful paper, worthwhile reading. I think I have a pointer to that at the end of the slides. So you might want to, read this in French if you can. So this was written, I think, around 42 or 43, but of course nobody cared about it because people were throwing bombs at each other. And then it was republished in 53 in the Berkeley Symposium, then in English. And it's an extremely well-written paper. It's actually better written than some of the others later on. Okay, so let's start with something very simple, namely XOR. Well, XOR, as we all know, is not linearly separable, right? So this would be XOR. Now, if I map this into 3 dimensions, so if I map it into x1, x2, and x1, x2, then I can see that this will make things nicely linearly separable. And so I can solve XOR. Now, I could do this, more systematically. I could ask, let's look at quadratic features. So phi of x, let's say being x1 squared, x2 squared, and then x1, x2. And for a sleight of hand, I'm using square root 2 x1, x2. And you'll see in a moment why this is a good idea. Because now if I take the inner product between phi of x and phi of x prime, I get that term here times that term, right? And so I can write this out, of course. This is essentially, x1 squared, x1 prime squared, plus 2 x1, x1 prime, x2, x2 prime, plus x2 squared, x2 prime squared, right? And if you squint long enough at it and hard enough at it, you will see that this is, of course, nothing else than x dot x prime squared. Okay. And this looks kind of magic, right? Because we had this gigantic mess of features that we extract, And then effectively, after you take the inner product, it's all really easy. And the good thing is this works for any polynomials of order d if I have just x dot x prime raised to the power d. And you can work that out in detail by explicitly expanding x dot x prime, and you'll see that basically if I want to get any polynomials, homogeneous polynomials of degree d, then the features that I use here are going to lead to exactly that. Actually, more than that, what I can show is that if I want to have features that are rotationally invariant, in other words, if I take x and x prime, and if I rotate them both in the same way, and if I want to make sure that the inner product remains unchanged, then this is the only scaling that I can use. So for that, you need to have slightly heavier duty group theory tools. You basically need to look at reducibility of representations in groups. But basically, what this means is this is pretty much the only canonical, straightforward, and meaningful way how to express this. Okay. And so, now we have some features for, second-degree polynomials, right? This thing here, right? That's basically all we have. So this would be, x1 squared, x2 squared, x1, x2. And you can immediately see that for the XOR, this is perfect because it'll exactly pick out these terms versus those terms. Right. That's XOR. Any questions so far? This is, I know it's kind of trivial, but it's actually conceptually quite deep. Now let's see whether we can watch this video. Let's see. It might just come on its own. Let's see. Okay. And so somebody actually went through all the trouble of, visualizing this, and yeah. So basically, what you do is you take, quadratic features, and while this is all nicely rotating, at some point in comes the separating hyperplane, which is based just a linear decision boundary, and lo and behold, now you can separate blue dots from red dots. And the guy had clearly way too much time on his hands, and I'm ever so grateful that I didn't have to run the simulation myself. So this gentleman with the name Udi Aharoni shall be eternally thanked for that. Okay, good. So, of course, there's a couple of issues there. Extracting those features can be really expensive. But, so for instance, if I have second order features in 1,000 dimensions, well, I can get a lot of numbers. And the solution is really to not go and compute those features explicitly, but you just try and compute the dot products implicitly. And for some features, this actually works. For a lot of them, you can't. And that's why people then don't use those features. So a lot of that is computational convenience rather than conviction that it's the right thing. And so now we get to a really important definition, namely that of a kernel function, which is a kernel is something that I can write as an inner product between, features of the data. So whenever I can do this, I will call this a kernel. This is not to be confused with a kernel of a kernel density estimator. Many kernels that we use in kernel density estimation are not kernels in the, reproducing kernel Hilbert space sense. So many kernels in kernel density estimation do not satisfy this. However, some of them do, and there is a bit of confusion sometimes for people that use this. Right. As a matter of fact, if you went and used a, density estimation kernel in this context, your algorithm may blow up. As in, it may diverge, it will not give you the right solution, it will do horrible things. So be careful about what you mean when you talk about kernels. About a decade ago, somebody sent me an email that he wanted to do his PhD with me, and he had substantial experience with kernels. And as a reference, he said that some of his code was in the Linux kernel. Okay, don't be that guy. Okay, so yes. I think we're essentially out of time. So what I'll just do is I'll conclude with a picture of the kernel perceptron, just the algorithm, because it works exactly the same way as before. I need to pack up because basically I need to be out of here in a moment. But we will pick that up again next Monday. I will not be around next Wednesday. However, there will be a substitute teaching this class on Wednesday. Furthermore, the videos will be up online for what will constitute Wednesday's class. So you can either come in and watch the show live, or you can watch it on YouTube, or do both. And then you can decide whether whoever will substitute for me on that Wednesday will do a better job than me. Most likely they will. Okay, thanks for your attention. Can you